these vacuum tubes were replaced by a semiconductor devices such as diodes. So in manufacturing of diode, knowing about all these basics about the semiconductors is very important. Dopants are nothing but the impurities that we add to intrinsic semiconductor to increase its conductivity in the room temperature. So to avoid these charges to move from one region to another region, we need to apply a potential, and we'll call it as potential barrier. Hello everyone, welcome to session 1 of chapter 14 Semiconductor Devices and Electronics. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. So in this session, we are going to study about the basics of semiconductor and semiconductor devices and the mechanism of how the semiconductor devices are fabricated. So without further delay, let us start with first the classification of metals, conductors and semiconductors. We all know the matter is classified as solids, liquids and gases. Now when coming to solids, we know that the atoms are closely packed in solids. So how does these solids are classified into? They are classified as metals or conductors and semiconductors and insulators. So based on the conductivity properties, the metals are nothing but good conductors of heat. So metals or conductors both are same, they conduct very quickly. So semiconductors means whose conductivity lies between the conductors and insulators. What are insulators? Insulators do not help in conduction process. Now in this chapter, we are going to focus more on semiconductors and its types. Say how this metals or the conductors, semiconductors and insulators are classified based on band theory. What do you mean by band theory? So we have a conduction band and a valence band. So valence band where the free electrons are present, conduction band after this free electrons move from valence band, it will go and stay in the conduction band which helps in conduction process. So this valence band and conduction band are separated by certain distance and we will call it as energy gap. So basically where exactly the free electrons are present? They are present in valence band. So now to increase the energy of these free electrons to get into the conduction band, we have to give them external energy. What is that kind of external energy? First one is temperature. So by increasing the temperature, the free electrons gain energy and they can move to the conduction band. So the another method to increase the conductivity in room temperature is doping. So we shall study about it later when we talk about semiconductors. Now first let us understand how these metals, semiconductors and insulators are classified based on band theory. So as I told, when it comes to conductors, the valence band where the free electrons are present and the conduction band overlap on each other. So when they overlap on each other, there is no gap between those two bands and the energy gap between them is zero. Energy gap is denoted by Eg because easily the free electrons can move to the conduction band and that helps in conduction process. This is coming to conductors. When we talk about semiconductors, the valence band is present and the conduction band above the valence band where the gap or the energy gap between this valence band and the conduction band is less than 3 electron volt. Because this energy gap is less, a very small number of electrons even at the room temperature can jump to the conduction band and helps in conduction process and hence the name semiconductors. Next is insulators. So in case of insulator, no conduction process takes place. So valence band and conduction band have a large energy gap and the energy gap between them is more than 3 electron volt. Since the energy gap is more, the electrons will not move from valence band to conduction band and they act as insulators. Because no free electrons are available in conduction band for conduction process and hence we'll call it as insulators. Now, what is the importance of studying only about semiconductors? Why the chapter semiconductors is introduced to us? Nowadays, we use all the electronic devices which are based on control flow of electrons. So, before this era, we were using vacuum tubes which were so bulky and very high voltage was needed for the operation and high power consumption. So bulky and larger area were required. So it was all the disadvantages. So to overcome all these disadvantages, so these vacuum tubes were replaced by a semiconductor devices such as diodes. So in manufacturing of diode, knowing about all these basics about the semiconductors is very important, and we are now using most of the electronic devices in our daily life which consists of semiconductor materials. So it is very important to know about this concept. So now we came to know what are the basic differences between the conductors, semiconductors and insulators based on the band theory. So now let us move on to only semiconductors. So we are just studying about semiconductors now in this chapter, not about the insulators and conductors. So semiconductors are basically classified into two types. One is intrinsic semiconductor and the other one is extrinsic semiconductor. So what is the basic difference between this intrinsic and extrinsic semiconductor? Intrinsic semiconductor is a pure form of semiconductor. We can say pure semiconductor. Say for example, silicon, germanium. So these are the basically or most used examples in case of intrinsic semiconductor. What are the characteristics of this intrinsic semiconductor? They are basically tetravalent. What do you mean by tetravalent? Tetravalent means there are 4 valence electrons. So these materials are tetravalent, which has 4 valence electrons, which means every atom shares one of its electron with the neighboring atom. So this is the basic structure of intrinsic semiconductors. So it shares one of the electron with neighboring atoms, which forms a covalent bond. So what happens to this as the temperature increases? As the temperature increases, this covalent bond breaks and one of the electron will come out as a free electron, and this free electron helps in conduction process. So to increase the conductivity in case of intrinsic semiconductor, we have to increase the temperature. As the temperature increases, the bond breaks. Here these covalent bonds, these shared electrons becomes very strong by forming a covalent bond. As the temperature increases, the bond breaks and the electron will come out, which helps in conduction process. So to get more number of electrons, we have to increase the temperature. In intrinsic semiconductor, number of free electrons is equal to number of holes. What do you mean by the concept called holes? As the electron come out of its covalent bond, there creates a vacancy. This empty space, we'll call it as vacancy, and this vacancy is nothing but holes which are positive in charge. So these electrons and holes are in movement always. They are not immobile. They are having mobility. So holes are generally positively charged and the electrons are negatively charged. So the number of electrons are always equal to number of holes in case of intrinsic semiconductor. How many electrons will come out of the bond? Those many vacancies will create, and hence a number of electrons are equal to number of holes. Now how to find the total current? When it helps in conduction process, there exists a current. So what is the total current in case of intrinsic semiconductor? That is denoted by I, which is equal to current due to free electrons and current due to holes. Because as I said, holes are also positively charged, and the current due to holes plus current due to electrons gives the total number of or total amount of current in intrinsic semiconductors. Now these intrinsic semiconductors, they act like insulators at 0 Kelvin, because at 0 Kelvin temperature, when there is no temperature, no bond will break and no electrons will come out of its bond, which helps in conduction process. When there is no free electron available for conduction, it acts like insulators. So even at room temperature, to increase the conductivity of this intrinsic semiconductor, we have to follow certain process, and that is nothing but doping. Doping means addition of impurities to this pure semiconductor. So when we add impurities to intrinsic semiconductor, we get extrinsic semiconductor. These are basically impure semiconductors because these are doped with impurities. The process of addition of impurities is called as doping, and the impurities what we add to intrinsic semiconductor is called as dopant, or they are called as dopants. So what are these dopants? Dopants are nothing but the impurities that we add to intrinsic semiconductor to increase its conductivity in the room temperature, and we will get the another type of semiconductor, that is extrinsic semiconductor, which are basically doped semiconductor. These extrinsic semiconductors are classified as N-type semiconductor and P-type semiconductor. So what is N-type semiconductor? How do we get M-type semiconductor? How do we get P-type semiconductor? So before understanding N-type and P-type semiconductors, what are the types of dopants we have? Let us understand. We have two types of dopants. One is pentavalent, the other one is trivalent. What do you mean by pentavalent? Which means the impurities has 5 valence electrons, and trivalent means we have 3 valence electrons. Generally, an intrinsic semiconductor is a tetravalent semiconductor, that is 4 valence electrons. Say for example, I have a silicon material. This is my silicon, and we have the tetravalent structure here. So each atom will share one of its electrons with the neighboring atoms to form a covalent bond. This is the general structure of an intrinsic semiconductor. When this is doped with pentavalent impurity such as phosphorus. Say for example, in the place of silicon, I am doping phosphorus. So this silicon will be replaced by phosphorus. What happens? Phosphorus is a pentavalent impurity, 5 valence electrons. So when this silicon is replaced by phosphorus, out of 5 valence electrons, 4 will go and occupy these spaces, and 1 more extra valence electrons will be remained, which has no space for its accommodation, and hence it will be a free electron. So this free electron will help in conduction process. So since we are having more number of electrons when the tetravalent material is doped with pentavalent impurity, one of the extra charge we are getting is electron, and the charge carriers, the majority charge carriers are electrons in case of N-type semiconductor material. Since the charge of the electron is negative, so it is called as N-type semiconductor. So in case of N-type semiconductors, the majority charge carriers are electrons and the minority charge carriers are holes. This is very important to understand. So why the majority charge carriers are electrons? Because it is doped with pentavalent impurity, which means 5 valence electrons impurity. So when the impurity of like phosphorus is added to a tetravalent, one of the extra electrons will be remaining, and this extra electron helps in conduction process, and extra is electrons, and hence the number of electron is more than the number of holes, and hence they are majority charge carriers in case of N-type semiconductor. In case of P-type semiconductor, say for example, this tetravalent material is added with or doped with a trivalent impurity such as boron. Trivalent means 3 valence electrons, so 3 will go and accommodate these places, and one of the place will be vacant. It is left free. So this vacancy is nothing but a hole. So when tetravalent material is, or when a pure intrinsic semiconductor is doped with trivalent impurity, the excess of charge we get is a positive charge, that is holes, and hence it is called as P-type semiconductor. Why the name P-type? Because holes are positively charged particles, and hence the name P-type semiconductor. So in case of P-type semiconductor, holes are majority charge carriers and electrons are minority charge carriers. So these are the basic examples, the basic explanation about two types of semiconductors, that is intrinsic and extrinsic. In case of extrinsic, we have two types, that is p-type and n-type. So how do we get p-type? By adding trivalent impurity to an intrinsic semiconductor. We get n-type semiconductor by adding a pentavalent impurity to a intrinsic semiconductor. Now let us move on to p-n junction. So what is this p-n junction? Just now we came to know what is p-type semiconductor material, what is n-type semiconductor material. As the name says, p-n junction is nothing but it is made up of p-type material as well as n-type material. So the junction between p-type material and an n-type material is nothing but p-n junction. So how do we obtain p-n junction? By adding trivalent impurity to intrinsic semiconductor to get p junction and pentavalent impurity to get n junction. So during the formation of p-n junction, so this is my p-type material and this is my n-type material, where in p-type material positive charge carriers are the holes are the majority charge carriers, and in n-type the electrons are majority charge carriers. So during the formation of p-n junction, the holes will get diffused to n region and electrons will get diffused to p region. So during this movement of charges, there creates a current, so which we will call it as diffusion current. The current due to diffusion of charges from p to n and n to p region, and this current is called as diffusion region. So these charges diffuse and they becomes immobile in a region called as depletion region. This region we will call it as depletion region. So this diffusion current is due to majority charge carriers, but as we all know, in p-type semiconductor and n-type semiconductor there are minority charge carriers as well. So because of this electric current which present in the depletion region, the minority charge carriers, that is electrons from this region and holes from this region, will get drifted. So the electrons will get drift to n region and the holes get drift to p region, and the current due to this drifting of charges is called as drift current. So these are the basic terms to understand in the formation of p-n junction. So the direction of this drift current is always opposite to the direction of diffusion current. So to avoid these charges to move from one region to another region, we need to apply a potential, and we'll call it as potential barrier, or it is barrier potential. So these are the basic information regarding p-n junction. So now this p-n junction can be connected to an external source and we will call it as biasing. So when the p-n junction material or p-n junction device is connected to an external voltage source, this process of connecting external voltage is called as biasing. What is biasing? Giving an external voltage to the p-n junction device is called as biasing. So there are two types of biasing. One is forward biasing and the other one is reverse biasing. We shall study about it in the next slide. So before that, we shall understand what is a semiconductor diode. A semiconductor diode is basically a p-n junction electronic device provided with two metallic ends for the external connection. So when this p-n junction diode, so this is the schematic representation of p-n junction diode, and the circuit symbol for semiconductor diode is this one, and this is anode and this is cathode, which means this is the p side of the diode and this is the n side of the diode. When this p-n junction is connected to a battery externally, it is said to be biased. There are two types of biasing, as I said. One is the forward biasing, the other one is reverse biasing. What is the basic difference between the forward biasing and the reverse biasing? When p side of the material is connected to positive terminal of the battery and n side of the material is connected to negative terminal of the battery, it is said to be forward biased. Similarly, if a p side material or junction diode is connected to negative terminal of the battery and the n side is connected to positive terminal of the battery, it is said to be reverse biased. So this is the basic difference between biasing, that is forward biasing and reverse biasing. So let us now understand the PN junction diode under forward bias condition. So when the PN junction diode is connected in forward bias condition, the P type of the material is connected to positive terminal of the battery and N side is connected to negative terminal of the battery. So this is condition for forward biasing. As a result, the effective barrier potential varies and the majority charge carriers are allowed to move freely across the junctions. So as a result, the width of the depletion region decreases. As the width of the depletion region is very less, the charges can easily move from one junction. They can cross the junction, which helps in conduction process. So as the conduction process increases, as we all know, the current through the diode also increases. So when the applied voltage reaches a potential called cut-in voltage, the current increases rapidly. We can write the graph of voltage versus current in case of forward bias condition. So in case of this, as the voltage increases, current will be constant. When the potential applied voltage reaches a cut-in voltage, current increases rapidly. So this is basically the graphical representation of a semiconductor diode when it is connected in forward bias condition. What is the reason for this rapid increase in current? Because the condition is applied voltage and the cut-in voltage will be equal. So when does it become equal? When does the current forms in the forward bias condition? When the depletion region width decreases, height of the barrier potential decreases and the charges can exchange or they can cross across the junction easily. So same in case of reverse bias condition, when the diode is said to be, or the PN junction diode is said to be in reverse bias condition, the P side of the material to be connected to a negative terminal of the battery and N side of the material to be connected to a positive of the battery. This condition is said to be a reverse bias condition. So when the diode is said to be in reverse bias condition, the majority charge carriers can stop flowing across the junction. As a result, the potential barrier width increases. As a result, the width of the depletion region increases and the height of the barrier also will increase. As the width and the height increases, the charges will not enough energy to cross the junction and there will be no conduction takes place in case of reverse bias condition. And hence we say that the conduction process will take place only when the diode is in forward biased condition. So in the reverse bias condition, the diffusion current is almost zero. However, there is a presence of minority charge carriers which will also give rise to certain amount of current. But in case of reverse bias condition, the resistance offered by the junction is very high and hence it will oppose the charges to flow across the junction. So this is the basic differences between the PN junction diode when it is in forward bias condition and when it is in reverse bias condition. In the next session, we shall learn more concepts about semiconductors and electronics. See you all in the next session. Until then, keep learning all of you. Thank you.